and I'm going to start the webinar. Oops. Hi everybody, and welcome to this next webinar in our urban scale building modelling series. I'm delighted to welcome Arno Schlueter and Zhongming, who are here to talk to us today about City Energy Analyst. Now, this is a different style of webinar to the previous ones on urban scale modelling, which have been a bit more theoretically focused. This one is very much focused on the tool, its capabilities, and what you can do with it. So hopefully there are lots of really exciting insights for you to take away from this. This webinar is part of the IBIPSA Education Committee's offering, and we exist in order to identify education and training needs throughout the building simulation community. We develop materials like this. We encourage other people in their development of materials, and we also like to offer training that is open to members and non-members as well, although we obviously hope that non-members will be inspired to join us after taking part in this. So the format today, I'm going to ask you a few questions just so that we can understand the audience a little better, and then I'll hand over to Arno and Zhongming for the presentation. If you have any questions that you would like to put to them, please can you use the Q&A box at the bottom of your screen, and I'll put those questions to them at the end of the presentation. And then once they've finished and we've been through the questions and answers, I'll tell you what's coming up. So I'm just going to start with my poll, which is just to understand a little more about you. So if you would like to tell us in what role you use building performance simulation, where in the world you're based, and what topics you would like to see in future webinars, we'd be really excited to hear all of that. It really helps us to plan our offering for future webinars as well. So I'll just give you a minute on that. I'll leave the poll running so that people can continue to add their responses. But after a minute, I will ask Arno to get on with the presentation. Otherwise, we will not have enough time for all of the exciting content that we've got planned. Okay, so Zhongming, would you like to share your screen and we can get started? I will stop sharing mine.
Oh, cool. And do you see my screen now?
I do. Thank you very much.
Thanks.
Great. So Arno, I'll hand over to you and look forward to hearing more.
All right, Zhongming, maybe you can go to the next slide already. So welcome everyone also from our end. We're happy to present today the City Energy Analyst, an open source tool we've been working on for quite a while now. I think it's a very interesting forum here at IBIPSA with a lot of practitioners and researchers to discuss these type of endeavors. With me is Zhongming Shi. He's the product lead of the CEA here at ETH in Zurich. Yeah, let's get it started. Maybe the next slide, Zhongming. So maybe to start you off, what the CEA is, it's an open source tool for urban building energy systems modeling, simulation, and optimization. So we're interested in buildings, but buildings in an urban context. We're interested in the interactions between buildings, the networks between buildings, and just in general, design and analysis that spans across multiple buildings to districts or even entire cities. It has been developed primarily for research and also through research here at ETH, at the Architecture and Building Systems Group, and in Singapore at the SEC Future Cities Lab. There's been quite some time and manpower going into this. We started this in 2011, and since then we have 5 PhDs and a lot of master students contributing to have I think a nice tool base which we keep on expanding. It's applied also in teaching and application projects, and this is what we will be focusing about. I will give an introduction, then Zhongming will go into the technical details, not too deep, but at a certain level, and then afterwards I will show some teaching application projects. But it has been developed as an application to inform decision-making and design. The architecture is an architecture that allows to connect this tool to different other tools, to more specialized models, which we will see in a minute. It's open source, which means you can download it at cityenergyanalyst.com for free. And even more important, it's supposed to be something we develop collectively. So the developer community on GitHub, you're also very much invited to join, to take part in the discussion and potentially also develop parts of the City Energy Analyst. Okay, next slide. The whole idea, of course, we do research on urban building energy modeling, on new methods, on new approaches, but this is really a tool which we hope to have impact. And you all know, I mean, we need to move fast. Climate emergency means we have maybe 20, 25 years to have significant change. But if you look at planning and construction industry, we see that that's not so easy. There's a big lock-in effect. Decisions that are made are valid for decades. And if you look into practice, you see that it's actually very few analytical and evidence-based methods that support this type of decision-making. That's on the tool end. On the other end, we see that stakeholders we work with often don't have access to these type of tool sets, and they also do not possess the necessary skills. And then on top of that, it's actually not so easy to acquire all the relevant data and data sets as an input to run these type of simulations. So that was our aim, to move from just basic research to application and implementation to essentially have more impact and actually change things. Next slide. CEA is a very distributed endeavor. Today, Zhongming and me are sitting here. There always needs to be some focal points, some nucleus, but of course we have a lot of people helping us in the development over the time. This is kind of the core team in Zurich. And in Singapore, but this is fluid and moving. We are very happy that we have different developers also contributing. If you're interested in individual contributions, you can go to the GitHub page and then everyone gets basically a clear idea who's doing what. But I think unique about this is that it's not only situated at ETH anymore, it's also spread to other universities, NUS, for example, or to the Singapore Future Cities Lab. But of course, we also do research. So Mariam Meshkinkia, for example, is one of our current postdocs that works on a Swiss project to further develop the City Energy Analyst. So it's going in both directions. Since 2022, we have roughly 1,400 downloads from 61 countries across multiple continents. And that is very interesting for us to see where this tool is actually applied and used for. We only started in 22 to track this a little bit. Before it was just open source, anyone could download. But at some point we realized we'd like to know a little bit more where and how this is used. And we can see that the most downloads are from European countries, Germany, Switzerland, but also China, United Kingdom, up to the United States, and of course the Asian realm. We also wanted to get to know our users a little bit better. This is why just a few months ago we had our first user meeting in Zurich, and it was really great to see a lot of people that use CEA in research, teaching, and application from all over the world, and we hope to continue that. We're proud that it's also used in teaching, at least in 9 international teaching programs that have lectures or studio-based courses working with CEA, so it works as a teaching tool. We also use it as a teaching tool, and I will show at the very end a small example of what we do with CEA in teaching. Next. Why do we go open source? We believe it's relevant to share these type of tools, the access to these type of tools. We are very fortunate that we work in Switzerland, but also in Singapore, and there's funds and information to do so. But of course, the world is a little bit bigger, and with open source and the possibility to contribute, we want to open this up, and we are happy that it has been basically accepted as one digital public good. There's a very interesting endeavor by the United Nations, among others, to promote digital public goods. And this essentially means anyone can use City Energy Analyst, can contribute to City Energy Analyst. It doesn't need huge amount of funds to actually get started. Next one. But of course, it's sometimes not so easy to get started. This is why we also think about how we can train people. We have user guides and courses on the website, but we also do user training. This is an example at the Future Cities Lab in 2018, where we worked with different stakeholders from universities as well as public and governance to train people on this type of analysis. And it has to go both ways, providing a tool, but also providing the knowledge to use such a tool and to interpret the results. I think this goes hand in hand. Next one. Just very quick as a framework before then Zhongming takes over and goes into detail. How is the CEA structured? It basically consists out of a selection of toolboxes, you could say, or different modules, starting with the data collection, demand forecasting, life cycle analysis, energy potentials, network design, and optimization. Zhongming will go into detail. What is important about this slide is that, of course, as you probably all know, it's impossible to make a tool that can do everything, but it's possible to make a tool that can connect to a lot of different tools. So by design, this has kind of a plug-in architecture, which means that CEA results can be used for connecting to other domains and disciplines, for example, transportation, such as MatSim, which is a mobility transportation modeling software, or energy hubs that allow energy systems optimization. We had projects that connected to the grid scale simulation, so nationwide, for example, electricity grids. And we're currently exploring the link to microclimatic simulation. So the question, how do energy systems, how do building energy consumption and production influence urban microclimates? And the idea for us as a kind of structural idea is that this is more like a tool ecosystem, and the CEA can be one part of this ecosystem. And now I would hand over to Zhongming to go a little bit deeper into the CEA.
All right. Am I muted? Thank you, Arno. So now I will take over to introduce a little bit more about what can CEA do. So at first, I want to define the skills CEA works on. As I can imagine, many of you come from an urban background. So for us, CEA work on multiple skills from building to district and all the way up to city. And the following slides, I'm going to show you the existing case studies that we tried with CEA in terms of skill or the numbers of buildings. And why we would like to work on mostly in district scale, as for example, this picture is like one super lofty green building in Singapore. Well, it can be green or as environment friendly as possible itself, but when it's standing in among other buildings and how in collaboration with the surrounding context is what we want to explore in the district scale. And as Arno introduced, CEA is an urban building energy modeling tool, and it does energy demand forecast. And on top of that, CEA does supply system design based on an energy demand forecast results and do optimization of the supply system. And we tried, when we designed CEA, we tried to minimize the input or the starting effort from the users to get simulation started. And I will introduce more detail about the input requirement to get CEA simulation started. As Arno introduced, CEA works on modular toolboxes, and in general, there are 6 modular toolboxes. There are data collection, demand forecasting, life cycle analysis, energy potentials analysis, network design, and supply system optimization. And if you ever tried CEA or you have we would try download CEA in the CEA dashboard, and these 6 modular toolboxes are located right here on the left-hand side. To go in detail about data collection, so as I mentioned, CEA want to minimize the user input, and we use OpenStreetMap to assist you to acquire the building footprints from OpenStreet for simulations. And as you can see here, this zone file with these buildings and the number of floor information, height information are all acquired from OpenStreetMap. Of course, if you have your own data prepared, you can always import your own building geometries and your own the building informations. And also we provide editor for databases, which I will introduce in the next slide why we have this database. But here is you can basically do all the data preparation within the data collection tab under the dashboard. And what is required for the building energy simulation for CEA? There are tons of data required. For example, the climate, the geometry, the occupancy data, and the system controls, and the building envelope information, and the impacts of all these construction components in terms of cost, primary energy use, and emissions. As you can imagine, if you want a district scale, if you want to collect the data for all the buildings, it's going to be a huge amount of work. And in CEA, we use the archetypal method, which reduce the minimum input requirement to only the geometries and zone. And you have to only know the occupancy in terms of the building use type ratios and the geometries and the construction year of the building, and plus our default or user-defined database by archetypes, and can populate the input data for simulations. And these archetypal method, how do we get this database? We use cluster buildings based on use type and historical data, and we can forecast like what could be like for a building built in a certain year and is residential. It can forecast most likely what could be the building components of this building and the thermal components, properties in the HVAC system and supply systems. And currently in the CEA, we have 2 built-in databases. One for Switzerland, and which is based on literature review and some local Swiss standards and EU international standards. And we also have the Singapore database, which is we built this database based on literature and the Singaporean standards. And currently ongoing, as we have many users in Germany, we have this initiative to include a German database in the following releases. As a summary of the CEA inputs, the minimum requirement is a zone file, typology file, which is the geometries and building use type ratios. And the CEA could help you to generate or to prepare the weather file, topography, surrounding contexts, and the street center lines, which is used for the network design. And also the secondary inputs, which is generated based or populated based on the databases. And the second modular toolbox is demand forecasting, and it includes 3 functionalities. It does building solar radiation analysis and create building schedules based on the database and also the occupancy of the building. And then eventually we do the building energy demand simulation. And we use this single thermal zone RC model and add a time steps of like hourly time step for each year, like 8,760 hours. And outputs includes space heating demand, space cooling demand, domestic hot water demand, electricity demand in terms of lighting appliances, and also the end use consumptions of electricity and gas, so on. And the model heat flows in the building and heat exchanges with environment based on physics. And as I mentioned, it's a single thermal zone, and the temperature resolution is 1 hour, and they can take occupant behavior into account and output detailed hourly energy services demand patterns. So this is the basic workflow with the minimum inputs. We create primary inputs and we calculate the solar radiation And then together with the secondary inputs and CEAs outputting the spatial temporal energy demand information forecasted. We use DaySim for solar radiation analysis. Then here's an example how we visualize in the CEA dashboard, how we visualize the solar radiation by windows, by walls, or by the orientation of a facade. Yes, like I mentioned, what we calculate, it includes thermal energy in both sensible latent format and electric energy and other formats of, like, for example, domestic hot water. And this is the visualization example from the CEA dashboard and how, like, one of way we visualize the energy demand results. How can these results be used directly and could be used for greenfield design studies? And you can study the impact of wind farm onto energy demand profiles. And you can work on retrofit studies and can understand the impact of building envelope improvements onto energy demand profiles. And how will the results be used further? Basically, all the following modular toolboxes are relying on these demand results. And yeah, of course, I will show in more detail. The next functionality includes the optimization of supply systems and optimization of urban design scenarios. And the life cycle analysis, we do both embodied and operational emissions analysis. And for the embodied energy, currently we're including the building construction components into consideration, and also we are able to consider retrofit scenarios. And for the operational emissions, that's relied on the energy demand forecast, and it comes in a format that the emissions based on the electricity consumed or some other forms of energy consumed on site. And the next knowledge or two box is about energy potentials, or on-site renewable energy potentials. And currently we have 6 functionalities. In terms of solar, we have 3 solar technologies, including PV panels, solar thermal, and PVTs. And we also do analysis of shallow geothermal, sewage waste heat recovery, and water body lake resource. And remember, we have the solar radiation analysis coming from the demand forecasting. And based on the solar technology simulation model, we come up with CEA output, the solar energy potentials based on the solar technology you selected. And this is the one example of how the solar technology input or profile look like. And user can, for example, this one is a generic monocrystalline panel, and then it comes in with these properties. And in terms of efficiencies, the cost, and lifespan. So as you can imagine, users can easily self-define additional types of solar energy technologies input into CEA and create customized simulation scenarios. And what is considered during the simulation, for example, the position of panels, is the panels on walls or on rooftops? What's the installation criteria? Are you installed PV everywhere, where there's a threshold for the irradiation on the building facade? Or if you want to install everywhere on the rooftop, where you want to install like 70% of the rooftop, and there's selection criteria helping you to decide where to place your PV panels or other solar technologies. And what else is considered? And the amount of direct and diffuse radiation on each panel is considered. Absorbed radiation influenced by the module type is considered, and the cell temperature is considered. And maybe the output includes the electricity yield mostly by facade, by building, and is also in an hourly resolution. Again, this is an example of one building or one district visualized using CEA dashboard for the electricity production of, I think this is a monocrystalline panel. And the next modular toolbox is about network design. And this is an example we made for a residential area in Singapore. And based on the street center lines that, if you remember at the very beginning, I mentioned there's street center lines that we as the primary inputs. So CEA will design a piping layout based on the street network, street center lines, and then simulates the operational status of these network and the energy distribution and sizing the pipe and substations. Here is one example. As you can see, these CEA decided the district cooling plant located right next to the anchor loads, and then CEA designed this layout and also sized the piping network. And the very last modular toolbox is about supply system design optimization, and use genetic algorithm and its multi-objectives. And objectives you can select is from 1 up to 4. And we defined objectives in terms of costs, emissions, and primary energy use, and also heat emission. The heat emission is anthropogenic heat ejected to the surrounding environment based on human or our cooling or any human activities. This is primarily for a hot and humid climate. As in Singapore, you can imagine that we want to reduce the heat rejected to the context, and we introduce these the fourth objective quite recently. So in the optimization modular toolbox, CEA will decide or propose scenarios of if you have a district heating or cooling network, which building to connect or which building to disconnect, and then also sizes the building scale technologies in terms of gas boiler, heat pumps, PV, solar collectors, as you select what it's which could be included. And the district scale technologies also help sizes the CHPs and free cooling thermal storage on a district level. And also, as I mentioned, which building to connect and which building to disconnect on the district level. So again, the 6 modular toolboxes are available more or less almost in a linear workflow on the CEA dashboard. As you can see, there is additional two tabs. One is some useful tools that we help you to get your data ready, and the other urban agriculture, which is part of these CEA ecosystem of where we're trying to make CEA extendable to any users. So we make CEA plugin ready, meaning that anyone can write their additional functionality and eject it to the CEA, the core CEA. And here I use an example of the urban agriculture plugin we developed for a satellite project. And if you're interested, you can go to the cityenergyanalyst.com/plugins to see a series of plugins that we know people have developed or are developing. And among them includes this agriculture plugin, and there's also additional recently we just added with the help of a researcher from Portugal, and we included a plugin for solar PV electricity storage. So if you're interested to develop a plugin for CEA for your own research project, always reach out to me and we can discuss how can like guide you or assist you on creating such a plugin. So much about the modular toolboxes. And just now I used the CEA dashboard to introduce the functionalities of CEA. Well, we as a CEA team, we always try to engage a multi-interface strategy. And you just see the CEA dashboard. We'll also see it comes in different formats, like you can use command line to call any functionalities of CEA, and the CEA comes in Windows and Macintosh versions. And also right now we are exploring, we're actually making the first step already to migrate CEA to the cloud. So this is a CEA dashboard. Feel free to download it and try it. It is available on Windows and the Mac. And also, like I mentioned, this is a CEA command line, which you can, for example, if you look closely with my console, if you type the command line, for example, CEA demand, and CEA will execute the energy demand simulations for you. As you can imagine, for all the functionalities, we have a command line for it. So you can create your own flexible script to execute simulations if you are like a developer or a researcher. Additionally, as we progress our program and we realize our tool was designed for researcher at the beginning, and then more people from practice and students and teachers and instructors are using us. And we realize many of our results are actually valuable for the general public. And this is a new initiative we introduced last year. We create a platform to circulate our results to the general public. And this one is we can, by answering a small survey, and the Singaporean residents could understand the farming potential of their balcony if they want to grow vegetables in a balcony by answering very few questions. Additionally, Grasshopper, I mean, as we are teaching CEA, we receive feedback, and there is a high voice that demand of CEA to be linked to Grasshopper. So CEA used to have a Grasshopper connection, and then we stopped maintaining it. And currently, we're considering reintroduce the possibility of linking CEA to Grasshopper again. And this slide shows an example of imagine you can create thousands of scenarios using Grasshopper parametrically, and you want to assess them, and these will be soon-ish available. In the upcoming release, we already have some provisionary link between Grasshopper and CEA. And in not too far away in the future, we want to introduce such a component. This is back to Grasshopper. So as a summary of my section, I want to reintroduce 5 points of CEA. The CEA is extendable. The extendable database will minimize the starting threshold for you to do simulations. But of course, you can always prepare all the data yourself. But using our CEA data helper and data management tools, and we minimize the starting threshold. And the second, CEA is fast and have detailed analysis at district scale. Most of the analysis we do is from 10 to 300 buildings. And very recently, we got to know in some master's thesis, students reach 30,000 buildings analysis using CEA. The third point is CEA is transparent, it is open source, and provides the possibility with easy integration with other approaches. And 4 is CEA engages a multi-interface strategy for CEA users of different modeling proficiency. And number 5 is CEA is plugin ready. And now I will hand over the presentation back to Arno.
Thank you, Zhongming. I will take over and show a few applications and use cases where CEA was used, both from our context, but also from people we learned that have been using CEA in their research and application. Maybe the next slide, Zhongming. One example is a research project here at the ETH domain, together with colleagues from other institutes, commissioned by the Federal Office of Energy. And the idea, our task basically was to assess future energy demands all over Switzerland. And for this, we expanded this idea of the archetype. So we moved from a building archetype to a district archetype, and basically assessed different scenarios. Maybe next slide. So the general idea of those use cases is more to understand how this has been used. I won't go too deep into detail. For most of those cases, they are also published, and you're very much welcome to look at the publications. But it's more like, okay, how would you apply CA in a workflow? What are questions you can answer, and how is this useful? So in this case, we did quite extensive surveying to identify those archetypes. And one was an urban archetype. There we used part of Zurich as a city, suburban archetype, a canton in the French-speaking part, and a rural archetype, more in the mountain regions. And then we did extensive interviews with those stakeholders and asked them how they would think their districts, the areas would develop. And this is what's shown to the right. So we, at the end, then established different scenarios based on their assumptions and on statistical data from Switzerland, how they would grow or how they would shrink in different cases and different scenarios. And then you basically come up with a projection of different use type mixes in this district over different scenarios and different years. So 2040, 2060, that was kind of the timeline. Next slide. And the idea, as you see, this is the starting point. And then, of course, well, it doesn't stand still. The urban building stock develops. So we had first to consider developed retrofit strategies. What would happen if you would have different uptakes of retrofit measures next to the different scenarios, development scenarios that Switzerland is kind of establishing. Then, of course, we have climate change already kicking in. We took 2 different climate change scenarios to take into account. And then we looked at those 3 discrete time steps, and that ended up in a huge amount of simulations. And at the very end, CEA is connected to the high-performance computing cluster at ETH. That's also an extension worthwhile mentioning. So we were able to compute a lot of calculations on the different scenarios. And then afterwards, of course, next slide, we can look how this then, what the impact of this is. And we can see, yes, as an example for cooling, there is a rise in cooling energy demand for all 3 district archetypes, as you would expect. But of course, it differs quite dramatically, both on the climate change scenario. Also, that is to be expected. But what is also noticeable is the change in different urban development scenarios, as they have quite distinct profiles on building use types, more commercial use types, for example, in the suburban case. That then very much influences the amount of energy that is required in these different archetypes and gives indications and leads on further infrastructure or on very targeted retrofit measures, how to balance this out. Also for heating, we could see that for some cases, especially in the urban and rural, there was a decrease of heating energy, as you would expect from climate change. But in suburban, it was actually an increasing heating because of the urban development scenarios underlying. So with the tool, we could kind of estimate how would things develop from an urban perspective and how would this interact with policy, for example, by retrofit strategies, or then with climate change, which is something we have to adapt for. Next one. Another very different example is what we did in Navi Mumbai together with our colleagues from IIT, Professor Chirag Deb and his team. And this was a very worthwhile example because it forced us to use CA in a very different way. Next slide. The idea here was that, of course, it doesn't make any sense that we sit at a desk in Switzerland and do this work. We would collaborate with a local team from IIT, with students there that would use CA and that would build up the database, but would also get in touch with the local stakeholders and see what type of interaction and stakeholder feedback we can get on these type of scenarios. Navi Mumbai experiences a huge amount of growth. It's a very carbon intensive grid, much higher than Switzerland. And then, of course, retrofit and renewable energy becomes quite impactful. Next slide. So this was one part of Navi Mumbai, Sampada, which was a district that was fast growing. And the first task was, as Zhongming already indicated, is of course acquiring the input data to run the simulations. To the right, you see kind of the Swiss perspective, where of course the national government provides a lot of data. And in other use cases and contexts, this is not so much the case, but it was not as scarce as we thought. It was different. Our hypothesis was, okay, there's not going to be a lot of data, but actually there was, but just from very much diverse sources. So one learning was clearly, okay, how to access different data sources to come up with these individual and first archetypes for this type of geographical setting. Next one. Then, of course, results that was presented to the stakeholders is, for example, then benchmarking the energy consumption of the existing building stock and of course, addressing also low income housing and the footprint of that and which type of building uses have the biggest impact. Also forecasting how this would develop or how much of this energy consumption could be covered by photovoltaics, for example, on the bottom, and what essentially this would mean for the carbon footprint. And you could see there's significant savings that are at reach, given the willingness, of course, of and governance to support that. Even there was some exploration what type of district cooling system could be used. But at the end, it was very interesting to see and pitch this to the local stakeholders and see their response to it. Next one, I have to move a little bit faster to not go over time. This is an example from our user day from Nora Funkhauser in the UK, working at Gensler, an architectural office. And she has developed a workflow for decarbonization strategies, as you can see here to the left. And explored that on a case study of 150 buildings, taking into account different data sources, similar as we did, and combining different tools for geometry modeling and analysis. As you can see here, also Rhino Grasshopper plays a role. And the idea was that in a design stage, you would like to see if you reach your carbon targets or if you go overboard, because this is actually the only time where you can influence pretty much your development. And she's done this very nicely, also visualizing then the results data of the City Energy Analyst. Next case. On the very opposite end, colleagues from TU Munich looked into energy systems optimization at district level, so not much about buildings, more about the networks behind it in a European research project. And the idea, again, was to provide early decision support. And they used CEA, as you can see to the top right, within a cluster of different tools. I used a database, an architect database, Tabula, which is a European Union database. Linked this to more specialized district systems simulations, and CEA was basically providing the energy demand profiles. What for us is always interesting is to see how does that match with real data, and in this case, they had really high resolution real data, and we could see that it actually fit quite well. There was, on the total demand, a certain deviation, mainly due to domestic hot water, but on the peak, CEA was able to come very close to the actual consumption data of those, I think, 3,000 buildings, and that was a very interesting case. And then last but not least, an application of our own work in teaching. This is from the Master of Integrated Building Systems. This was just last fall, where students were tasked to develop one part of Zurich in Altstetten and develop a base case assessment. So doing the legwork of retrieving the input data, as you can see to the left, and analyzing structure, histograms, for example, on building ages, systems, different systems types and sizing, occupant density. Then they used the modules for energy demand and solar potential, as you can see in the middle, to develop an energy supply strategy based on renewables, investigated also district heating networks. And then to the right, they came up with a process how to do urban redevelopment and retrofit. As you can see here, this student group invented this little game, how the user could be convinced to actually do that, and how this would then progress over the different decades, and what this would mean on an emissions target and timeline. These are use cases, and then next slide. Yes, fine. Last but not least, we want you to join. The whole idea of CEA is that this is a community approach, and we embrace very much the contributions from our community. And you, of course, can download the tool and learn anything else on City Energy Analyst. And then, of course, if you dig into, you can also assign to the forum and to the GitHub exchange. We have newly, since a year now, a CEA Newsletter. If you're interested, and if you download, you get automatically included in the CEA Newsletter, where we inform about recent developments and also provide a forum of what people are doing. The main idea is really to exchange. If you provide input databases someone else could use, for example, and this will all be posted in the newsletter. I think that was the last slide. Thank you very much. We took a little overtime, but thanks for your attendance, and I think we're happy to take some questions.
Great. Thank you very much for that. That was absolutely fascinating. And I know I have some questions of my own. So if we get through these quickly, maybe I can squeeze one in from myself as well. We've had a couple of questions which are about the physics behind the buildings and energy calculations. And I wonder if you could just explain again how that works in CEA and why you chose that approach above other approaches which are used in, for example, Energy Plus.
Zhongming, you want to take that one?
Oh, sorry, I got a bit distracted reading the Q&A section questions, and I didn't hear the first half of the question.
The first question, why we chose the RC modeling approach, or the physics behind.
Well, for this question, for myself, I mean, I haven't. Arno, would you take up this question because
Sure.
it was
I mean, the decision was based at the very beginning. We actually had a first exploration with a different tool set that used Energy Plus for each simulation, but we decided on a simplified dynamic thermal RC model because of the speed and the ability to reduce input data for the calculations. At the end, we wanted to have something that can be rather quickly executed. Bear in mind, this was 2011, so computational power was also a little bit more reduced. And we found that this is sufficient to do this larger scale analysis, also based on the experience that we worked for about a year with very detailed Energy Plus simulations, so high resolution white box models. We opted then for RC models. And I guess for both, there's pros and cons, very clearly. The amount of detail is reduced in our approach. And also in RC kind of lumps together a couple of parameters that is not so ideal as compared to like fully resolution white box models. But in our case, it proved to be, I think, quite handy. And what we've seen, of course, we did the validation and compared it against white box models such as Energy Plus. And we've seen that in the aggregation, of course, individual errors tend to cancel out or tend to be reduced. Of course, if you look at the individual building, then, of course, if you want to know detailed specifics about the individual building, then a high resolution model is probably more helpful. For us, it just was a good trade-off of calculation speed and accuracy, but we're always working in kind of, changing, altering, amending. So it's always work in progress.
Thank you. And just to come back to a point you just mentioned there, how do you perform verification and uncertainty quantification on the model? You talk about validation against Energy Plus models, for example.
Right. So we have different steps in that. Obviously, it's unfortunately not so easy to get the granular data of larger districts to run a full-fledged verification and validation. So it starts by comparing to models that have been validated, such as I just mentioned, to Energy Plus at the very beginning. And then we are also increasingly using the case studies. We try to employ the case studies to understand and kind of at least obtain information about plausibility of the calculations. For example, in Zurich, we had some quite aggregated data, which we compared it to CEA, and we were able to notice the deviations. And now, as just mentioned, this case study TU Munich actually had high resolution data from 3,000 buildings, and the results were quite encouraging. But this is, of course, an ongoing exercise. We hope to embark. We still dream of this fully monitored, fully measured, and fully accessible district that would provide us all the data that we have. I think we always have to be critical with this type of simulations and always check for plausibility. In the past 10 years, we had multiple studies where we've seen, okay, we are not, it seems to be quite okay, but of course we don't have this perfect validation case yet.
Yeah, I think it's worth mentioning perhaps that this is a topic that's being discussed as a potential IBIPSA project, the development of the validation data for for these larger scale models. Obviously, we already have the best test approach, which is very well used and developed over the years. There has been the recent project on desk test, but there's a need for more, and that's under active discussion at the moment. And I'd welcome you to join the conversation if
Yeah,
you
we'd happy
already.
to. We just actually this next week we're discussing a potential case study that would actually have a very, very good situation on obtaining data about the buildings as well as measurement data for the next 5 to 10 years. So that we hope we're in reach. That's what we hope. But we're
Amazing.
happy to discuss on that. Yeah.
Yeah, that sounds like an amazing resource. Can I ask a little bit about missing information? In particular, one of the key challenges with any of these models is about understanding the refurbishment status. Understanding the age of a building is one thing, but whether or not it's still in its original condition is a completely separate question. And how do you address that?
Yeah, sure. Zhongming, you want to?
Yeah, sure. So the existing buildings that like we mentioned, we use this archetypal method that that's basically you can imagine we did a survey of the existing building stocks and come up with the archetypes of if it is built between a certain year, for example, 1980 to 1990, and it's an office building. And then we come up with an archetype that it's more or less representing the typical buildings of that type of profile of buildings. That's how we do that. And like just now, as Arno mentioned in the validation part, as we work on a district scale, a lot of the granularities of the data were cancel out when we work on the district scale. Yeah, that's how we mean the missing information is completed by the assumption that we use some archetypes. Yeah.
But maybe to add to that, I think this is also one of the big topics, obviously, to get more granular data. In Switzerland, we have a couple of databases we can access, and we use those databases, but they're often self-maintained, so it's always not all clear if this is really the correct data on that. We also did explorations on acquiring data automatically. I mean, there's a lot of attempts, not only us, but other people are looking into flying drones and using thermal cameras and to understand more of this input data. And I think there will be some interesting development of accessing more better access to urban data at some point. Yeah, I think this is under development. What is interesting in this Navi Mumbai case was more like what specific data is missing in the individual context. And for example, for Navi Mumbai, we were able to retrieve almost everything, but one thing we really got stuck, and that was the building height, something that is basically a very simple parameter, but dependent on the geographical context you are, of course, you have limitations of what you can access and whatnot.
Thank you. I've got a couple more questions in the chat. There's one hand up, and I would invite you to put your question into the Q&A, please. So I'm going to try and do these 3 questions that we have here and possibly one more. I've got to leave myself a little bit of time to tell you what's coming next as well. But this question, the next question is, I think, perhaps related to the question about refurbishment status, or perhaps the method is the same, but how do you model multi-use? For example, the case where you have shopping in the ground floor and residential accommodation above that, and potentially even more complex than that.
So
I can answer, but Zhongming, you can.
Yeah, so we do have the capacity of model multi-use buildings, and in minimum input data, we require the user to define if the building is have 20% residential, 30% retail, and 50% gym or other functionalities or use types. So that's how we define the multi-use buildings, but we see it does, as I mentioned, we use single thermal zone. So you will take the most of the properties from the main use of the building to apply to the model. And of course, the occupancy information of the other uses are included, but for the single thermal zone restriction, that we only will consider mostly the main use of the building.
Thank you. That's really helpful. Can you perhaps elaborate a little bit more on how you deal with the CO2 emissions or the equivalent CO2 emissions, and whether you currently take into account other aspects such as land use and material use?
Yeah, so I mean, CEA right now focuses on the operational emissions primarily. So what is calculated as an energy demand and end use, and the different utilization factors for the technologies to provide this. We've had from the very beginning on also information about embodied emissions of buildings. This was very rudimentary, to be honest, and we are now expanding this as part of a research project to have a more refined approach to capture the energy relevant embodied emissions. So the attempt is not to have the full LCA of a building, but to look into the embodied emissions of envelope properties as well as building systems, to get an idea what the interactions of the effort we have to take to create this heat or this electricity versus the embodied emissions that are taken up to actually provide it is. So it's a very focused approach. We're currently discussing linking CA to another tool that is developed here at ETH that does a very, I would say, mid-level resolution LCA analysis for the entire building. But then, of course, the question bounces back to the question of archetype. Then, of course, you need to have much more information on the individual building about structure, for example, about other properties of the building. So right now we're trying to really focus on the energy aspect of it and calculate operational and embodied for energy relevant components of the building, of the multiple buildings.
Thank you. I think I've only got time for one more question, which is to ask how you set the resolution of the data and the parameters when you conduct the district level modelling. Obviously, urban data often is in at very different spatial resolutions depending on the individual data set. And how do you address that?
Well, I mean, like we mentioned multiple times, that based on our experience, compared our simulated results and measured results, well, most of the time on district scale, the errors cancel out each other. And then we do, for example, on the district scale, when we consider building to wall, for example, window to wall ratio, and we'll consider like by orientation of the facade, and that's what we reduce these granularity to go into more detail, which exactly facade have what type of window to wall ratio. For example, that's how we reduce the granularity of the input data for our model. What else? And Arno, do you have additional comments on these?
I think that's great. It's such an interesting topic. I think we could easily keep going. Now there is one more question, and it's actually conveniently the question that I would have liked to answer. But what I'm going to do is instead suggest that perhaps we have a conversation about this separately, because I think this is an important topic for IBIPSA as well, the Education Committee, which is around the education on urban scale modelling, which is a particular interest of mine as well. So we will, if you don't mind, we'll have an email conversation about that and perhaps a meeting later. I would just like in the last sort of minute and a half to let the audience know about what's coming up. So we have another two of these tool-focused webinars which are coming up. We have one in March, which is Christoph Reinhardt, who'll be talking about UBEM.io. And then in May, we have Jerome Kampf, who's going to be talking about CitySim. And these are both the sort of practical explorations of the tools and the workflows. And you can use the QR codes there to sign up for those. And the links will also be circulated on LinkedIn and on the IBIPSA mailing list. The big event for this year is going to be a new webinar series on occupant-centric simulation-aided building design. We are very, very fortunate to have all of the experts behind the book who are going to be doing webinars on the individual chapters, which is very exciting. And we're going to be kicking off later this month with a panel discussion. So what would you like to know about occupant-centric modelling? If you use the link here, you can go to a quick survey where you can put in your questions. You can vote about the questions that others have raised to see which ones are most interesting to you, and you can sign up for the webinar itself as well. So please do that. The recording for this session is going to be on our YouTube channel at IBIPSA University. The recordings for all the webinars are on there. It's an amazing resource, almost a complete education in building performance simulation. So I would really encourage you to have a look through all of that through previous webinars as well. We're up to about 50 videos on there. And finally, if you have enjoyed this and found it useful, I would encourage you to consider joining IBIPSA as a supporting member. Our supporting members obviously support the work of IBIPSA, including things like this webinar. They receive a print subscription to the Journal of Building Performance Simulation, and online access to the journal, and you can use the supporting member logo. The fees for this are remarkably affordable. These haven't changed since about 2018, so now would be a good time to sign up before anybody else notices that they haven't changed the prices for a while. But with that, I'd like to say thank you very much to our speakers, to Arno and to Zhongming. Thank you so much for an incredibly informative and interesting session. And thank you to the audience for your very insightful questions. And I do hope to see you again soon. Thanks all.
Thank you very much.
Thank you.